Are you looking for me,
Oh,
Lucas?
yes, all
Yeah,
good.
sorry.
We got too
I
many
just
names here.
cannot
Okay,
share
sorry, I was just
my
scrolling.
screen with you.
Awesome, perfect. Yeah, so welcome from Vancouver, the unceded traditional territories of the Musqueam, Squamish, and Tsleil-Waututh nations, and I welcome everybody from wherever you are. My name is Lucas Aronson, and I'm a principal geotechnical engineer here with BGC, and also BGC's cryo co-lead. I've been working for BGC for about 17 years, and it's now my great pleasure to introduce our second keynote speaker, that will bring everything home, and that is Dr. Pooneh Maghoul. Pooneh is a full professor of geotechnical engineering and the founder and director of the Sustainable Infrastructure and Geoengineering Research Laboratory, the SIGLab. She's also partner of their partnership and communications of the Space Resource and Infrastructure Engineering Research Unit, Astrolith, at Polytechnique, Montreal. She's currently still serves as VP Finance of the Canadian Geotechnical Society, director at the Mars Society of Canada, and co-chair of the Geotechnical Engineering Foundation Group of the ASCE, Lunar Engineering Design, Analysis and Construction. Most recently, she started as a lead in sustainable infrastructure in cold regions at the United Nations University Institute for Water, Environment and Health. But this shows a little bit what Dr. Maghoul's research interest and focus is, which is on the sustainable development of infrastructure resilient to climate change in harsh environments, and not just here on our planet, but far below into the moon or extraterrestrial into space. She works on permafrost engineering, geostructural health monitoring, and in situ resource utilization, so the ISRU. And she's been a recipient of multiple awards and has over 13 patents and software licenses. I met Pooneh several years ago, and I think we quickly identified there's a lot of interest, a common interest, and for partnerships that we now have between BGC and her group. And this led to some of the research that she will be presenting, amongst other areas, because it mostly related to the challenges of how can we be, as geotechnical engineers, more sustainable, as well addressing the challenges from extreme climatic conditions and greenhouse gas emissions. I also want to highlight quickly that this is only one part that we're collaborating, but the BGC is also working on other nature-based solution problems. And specifically, we are interested in using microbial activity to stabilize mine tailings as well and store carbon. And this is an initiative that has been done in collaboration with Dr. Sue Baldwin and Dr. Med Imran at UBC, where we're exploring the idea of cementing mine tailings. And my colleagues have presented a paper at last year's Tailings and Mine Waste that shows how tailings from mine sites in Canada can be increased by the mechanical performance. And they also demonstrated that microbes with metabolic capacity exist naturally in a lot of mine sites. Furthermore, the Mining Microbiome Analytics Platform, short MMAP, is currently developed with partners of Rio Tinto, Teck, UBC, BGC, Kunki, and Alonia. And this is an online library and analysis tool where we tackle the complexity of microbial solution development for mining. Mapping the metagenomics, it's been out there for many, many years, but about 15 years ago, it cost about 100,000 to create such a map, but now we're down in the hundreds of dollars, so it makes it quite efficient to start mapping the metagenomics, and that's the idea of a map. And this fits into BGC's vision for the future, where we can use tools like MMAP to provide unprecedented insights into the microbial communities at various sites, and then develop sustainable solutions such as bioleaching, biocementation, and corrosion mitigation across a wide range of industry and areas. And with that, I'd like now to pass it over to Pooneh to give us a little bit more of an insight on nature-based solutions for stabilizing problematic soils. And yeah, thanks very much for taking the time out of your busy schedule. Over to you.
Thank you very much, Lucas. I always have time for you at BGC. You are very lovely people overall. Thank you very much for the opportunity. My name is Pooneh. I think Lucas introduced me well, more than necessary, I think. And this is the topic of my presentation today, nature-based solutions for the stabilization of problematic soils. It's a video. I cannot talk about the moon and beyond, but let's just start, who knows, maybe next time. Yeah. Before I go through what we do, I just want a little bit talk about sustainable technology, and just a little bit about the vision behind what we do with BGC, because it will open lots of opportunities for collaboration and brainstorming, of course. And let's define sustainability. I always have this, discussion with many people that when we talk about sustainability, we are not necessarily talking about resiliency, and it's very important to actually define terms correctly. Then if we want to define sustainability in ground engineering, it involves long-term performance, durability of structures. We want to recycle waste. We want to consume less. We want to have the minimum environmental impact. And The thing is that we are in geotech, we work with soil, we work, in underground spaces, and unfortunately, at the end of the project, no one sees what we left. And in terms of carbon footprints, I have no idea. I couldn't find specifically, statistics on the carbon footprint in geotechnical projects in groundwork. For example, when it's related to the structural engineering, it's above ground. Everyone can see it. Then we have a better idea about these carbon footprint, structural elements, etc. But when we deal with ground engineering, groundwork, earthwork, I believe it's a bit difficult to actually specifically give the numbers. And we know that construction and the built environment accounts for about 40% of global greenhouse gas emissions. Again, I have no idea if specifically we want to talk about earthwork, what would be this amount in terms of environmental impact, greenhouse gas emissions, etc. Then if you look into the literature and search, about this sustainability or improving the sustainability of a project, you can see many things. For example, waste management, infrastructure development, and rehabilitation. The idea is that we want to reuse. We don't want to leave things. For example, if we have an aging structure and we want to rehabilitate or completely destroy it and build a new one. What if we recycle, the existing foundations? What we call it foundation reuse. And all of these, the small elements for sure contribute to a carbon footprint of a project. Resource recovery, mitigation of natural hazards, frontier exploration and development, energy efficiency. For example, how we can recycle this heat island in urban zones. Everything related to geothermal, shallow geothermal extraction, etc. They will contribute to this circularity and sustainability of a project. Then I took it from LinkedIn. I saw it. It was a very nice post. The person who shared this post, that person is not in geotechnical engineering, is in climate finance, climate policy. But the message was very clear. Takeaway, it was last year, takeaway from COP28 to reach the 1 degree target. We need to transform our economy at the scale of the industrial revolution, but at the speed of the digital revolution. In order to do so, climate technology is key. Then now look back, to geotechnical engineering. And when we say climate technology, what does it mean? We all live in big data era, AI, era. But the main question I have is that, in my understanding, I use AI a lot too. These tools can help us to analyze better, to understand data better, but it doesn't mean necessarily that it can gives us a kind of hard tech, tangible products. We can integrate AI in those things, but when we talk about specifically ground engineering, the technology, how we can revolutionize, the way that we practice geotechnical engineering. Now, the big question is that climate technology in ground engineering, we can develop it. I'm a researcher, I'm a professor, I developed lots of fancy things. We want to explore even the moon in our lab, but how we can, do technology transfer and bring all this development to a real life project and technology adoption. Then there is something that we know less, unfortunately, in geotechnical engineering. It's this scale, we call it technology readiness level. I don't know how many in this room about, this readiness level. There are so many things, application readiness level, scale, etc. Normally, what we do in the lab, we do literature review, we define the methodology, we do that scientific, approach. We develop prototypes in the lab, we test it, we do like lab scale test, physical modeling test, and we stop somewhere here, 3, 4. The technology that you use, for example, this AI that we all use, it's here, 9. All these instrumentation that currently we use in practice, they are all 9. Then now I want to develop something. I am in here and I want to bring my technology to 9 and give it to BGC and BGC clients, to apply it in a real life project. Then we have lots of, this development level to be done. I'm just telling you because the things that you will see later on, it can be seen like, I don't want to use science fiction, but we do, the lots of interesting things. And the technology readiness level for now, it's somewhere in here, 3, 4. Then if we want to use it, give it to BGC clients to use it, we have to develop it further. We have to test it in the field and make sure that all the steps that all these, the application, it makes sense and we can make this technology works in a real field. Then problematic soils and SOSTEC. Then when I talk about this problematic soil, better than me what I talk about, all these, the permafrost soils that we can find in northern regions. Does it work? Yes, this is permafrost thaw, as you can see, and we have retrogressive thaw slump. And the problem with geotechnical engineering, all these geohazards, is that we deal with large scale problems. Then it's not like doing at a smaller scale and fix a problem. It's larger scale. We have to develop technologies that can be applied in, the natural conditions and at larger scale. The other thing, problematic soil is tailings. We just there were a few presentations before me how we can actually mitigate it, liquefaction, all these erosion problems. You're in BC mostly, then you're okay, but this is the condition of our road that we have, in Canada. How we can actually develop a technology, green technology with the, minimum carbon footprint and environmental consequences that can stabilize things. then it doesn't mean that we don't do anything in geotechnical engineering. We do lots of interesting things. For example, we do mechanical improvement through dynamic compression, preloading. We have all these chemical stabilization methods. For example, chemical stabilization, these things, forget about it. That biological stabilization that you can see, we started, working on this biological stabilization, I think for 20, 25 years now. And now we try to apply it in the field. Then lots of, behind this biological stabilization, it's at least 20 years of hard work, lab development, and now we are at the stage of using this technology in real life projects. What we tried to do here is that even that biopolymers, nanomaterials, we are now again at the lab scale. We are not in the field as far as I know, and we are working on these things. In terms of chemical stabilization, the TRL technology readiness level is very high. It's 9. It is, I think, as much as used as this mechanical improvement, dynamic loading, preloading, etc. But again, how we can develop new methods, sustainable technology, green cements for soil stabilization, for stabilization of problematic soils. Cementing of soil particles to boost their strength, create a solid structure is one potential solution. Cementation, but by using green methods, nature-based methods. And we know that cement production involves a process emitting significant CO2 and requiring high temperatures. We want to avoid it. And what we try to do at the end is that to find a kind of recipe formula that we can create, we can make this precipitation of calcium carbonate crystals inside soil pores to make this cementation between particles, make ground improvement, and improve the physical and mechanical properties of soil. Then what we have done with BGC is that we tried to find all these waste, industrial waste, agricultural waste, mine waste, and also use microbes, similar to what we do as MICP, microbially induced carbon calcite participation, sorry, and bring new ideas in the recipes, in the formulas. For example, what for that MICP, I don't know if you know that, but for 20 years, almost everyone have been working on the application in granular soils. Why? Because we cannot use MICP in fine grained soils, in clay soils. Then you see that from the beginning we have this barrier, then we develop a technology, but we cannot use it in all types of soils. But what if we use the kind of additives that make it work? That MICP, we can use it even for clay soils. That's why we tried to mix MICP with nanoparticles, with nanotechnology. For example, SiO2, silicon dioxide, silica, or even calcium carbonate. Use, these onion peels, use brewery wastes, eggshells, or even zeolite, and develop MICP with different additives. EICP, which is the enzyme, it doesn't come from microbes, but for example, beans, soya, or even using fungi. Or the other thing that you can see, MBC, we call it mycelium-based composite. Create those fibers, dynamic fibers that can grow within the soil and bond these particles together. Then if we can develop different recipes, different formula for different types of soils, we can somewhat deal with the complexity of the nature. We can use it in tailings, clay, till, permafrost soils, etc. I know that Lucas hate when we say permafrost because permafrost is a thermal state of a soil. Then I added permafrost soils. Then what we do normally, again, technology readiness level 3, 4. Then here I'm not talking about field test because we still need to develop the recipes and work on different aspects of it and see if it works well in the lab, then do after physical test and then go to the field. Then what we do here, I just gave you one example, MICP enhanced with nanoparticles. We tested on clay soils. This is our methodology. We did some macro scale tests. We did element tests, uniaxial test, triaxial test, because we are in cold regions. Then we actually tested under freestyle cycles too. And then larger scale test, I mean, check table tests, centrifuge test, physical modeling. And we also performed macro scale test because we want to see at microstructure what is going on. Then we did SEM, XRD, and also chemical analysis to make sure that the chemical things that we see within the pores, it's exactly that calcite crystals that we were looking for. Then the example here you can see for now, example one is related to nano-enhanced MICP for clay stabilization. We did mixing in the lab. We prepared our soil samples. We put them in a mold. This is the picture of one of our samples. We put it here. You can see the image of uniaxial test, and we tested it with different percentage of nanoparticles. We tested it. The sample is fully saturated. One of the biggest issue with MICP is that when the saturation degree is really high, it becomes less efficient. But by using, different additives, we could manage actually, and we saw that, when we use these additives to MICP process, the peak strength increased significantly. We published our work. We also did freestyle cycles of the samples. And here, what you can see is at the macro scale, you can see actually this calcium carbonate created within clay minerals. It was actually a big deal to be able to stabilize clay. I told you MICP have been used in coarse grain soils, but clay very limited applications. But adding those additives, including nanoparticles, we could make it work. We also did centrifuge test. As you can see here, this is our model. Through deep mixing, we injected these solutions in the soil and then put it in a centrifuge test just to why we use centrifuge test. The sample was about 50 centimeters. Then through centrifuge, we could have an idea about the stability of an 11-meter slope. Then this is the results. What you can see here is for untreated ground. We just wanted to have a benchmark to compare the treated soil. Then here you can see that by increasing G, you can see the instability issues that we could see. But when we treated, the soil, we injected, you can see in here the injection deep mixing, you can see that even at 77 G, which is equivalent about 12-meter slope, no change. It works quite well, and we're very happy actually about these results. We also tested another formula. It is based on EICP and mixing with zeolite. We add other additives to it too, but we tested it on tailings. And as you can see, that black line, it's for untreated tailing, and you can see how the using EICP method plus other additives increased significantly the strength of tailings materials, tailing soils. This is actually the product of what you can see, the biofibers that we created in the lab. It was a very, very funny sample. It's, I think, after about 28 days that you can really see the creation of these biofibers within the soil. It's in a dynamic, way. Keep growing if the conditions are still available. Then it just bond these particles together and increase significantly the strength of the soil. And also for permafrost, this is my favorite ones. We tested on peat ice-rich permafrost. We thawed in the lab. You can see this is soil. This is the amount of water we had. It was actually the slushier than a slush. And what we tried to do is that you have like a bag of water mixed with a little bit soil, and now they ask you to stabilize it. Exactly the same thing that we see these days in northern regions. We developed our solutions and tested different things. For sure, for the first round it didn't work, but we tried to develop again new formula, new recipes. And what we tried to do is that put it in a little capsules, as you can see, and leave it, here on top of the water, you can see. And it just started drinking, absorbing water. And this is after, I think, after, if I'm not mistaken, 14 days. And these pictures, I took it 2 weeks ago. Then it's like, make it like a rock, soft rock for now. We have to still wait and see what is going on, but it's in process. It's a dynamic environment and increased significantly. At least when we touch it, for now, we have not carried out any lab tests. We are still waiting. Uh, But when you touch it, you cannot compare the strength of this with what we had here. Then if I want just to in general make some comments about this development, we can use nature-based solutions, circularity concept in ground improvement. I should emphasize for now the technology readiness level is 3-4. We are not more than that. We are not still ready for field trial test, but within 1 year, 2 years, for sure, we will be there. And one of the things that we have to think about is how we can scale up at engineering scale. For now, again, I repeat, we are in the lab in centrifuge test, but now imagine we want to bring our solutions to an engineering project. It can be done, but we have to think about the way that we want to actually use it in the lab. Is it sustainable or not? We test everything, all the steps, all the ammonia, everything that, the released from these processes, we try to test it. And if we feel that there is something that can be dangerous environmentally, we try to mitigate it. But what I want to say is that sustainability is not all about materials and residuals. It's also about the cost of the project. If we have the best solution, but it's costly, no one will use it. Then how we can actually make it possible? We are working on it. I don't think that it is expensive, especially if today I compare the cost of the project with like Portland cement, but with all those carbon, taxes that we have, it will change. Um, I just want to acknowledge those who contributed to this project, including BGC. BGC has actually a very important role in this project. Thank you very much. And also my PhD student, Sarah, who is actually just an excellent student. Thank you.
Thank you very much. Yeah, and that's kind of the end. I think we have time maybe for 1 or 2 questions if there's anything in there. I haven't seen any question. I will still ask you because now you've been talking about getting this into the market, and I think we have the opportunity here with some of our clients, some owners, users, engineers, scientists here. So what do you think is needed to accelerate to get these products into the market? And just thinking that we don't have necessarily the time to wait another 10 years to start implementing some of those solutions.
Logistics, that's all. you know, I mean, you tell me that there is a site, we want to test it, we will make it happen. You know, I mean, it's just the kind of coordinating big projects, ambitious projects. We work in a field which is really risk averse, and I agree with it. I don't want to say why we are like that. We have serious projects with, you know, the bad consequences if something happens. But what I want to say, answering your question, I think logistics, having access to a site, especially, you know better than me, Lucas, when we work, you know, in up north, we have to make sure that communities accept. We cannot bring it to their community and use them. We have to actually do kind of awareness, introduce the technology to communities, not necessarily northern communities, all the communities. We have to introduce what is green cement. And green cement, we have to, when we say green cement, everyone for sure is happy because we think that environmentally is okay. But we have to provide realistic information that sometimes environmental consequence can be as bad as cement. We have to be honest for sure. And logistics, to me, for now, it's the biggest, you know, it's not an issue or a problem or concern, but we need to have access to a real site and coordinate, you know, the implementation of the technology.
Yeah. No, thanks so much. No, these are very, very important points.